How does delta V affect orbital insertion? Imagine trying to land a paper airplane perfectly on a specific spot on a table. You need just the right speed and angle to make it land smoothly. In space, spacecraft face a similar challenge, but instead of paper, they relying on precise velocity changes. That's where delta V comes into play. Delta V, which stands for change in velocity, is a key number in space missions. It tells us how much speed a spacecraft needs to reach its target orbit. Think of it as the fuel and power needed to get from one path to another. When a spacecraft is launched, it starts with a certain velocity, but to settle into a stable orbit, it must perform a burn with its engine. This burn increases or decreases its speed by a specific amount called delta V. The amount of delta V used during orbital insertion determines the shape and size of the orbit. For example, to go into a low Earth orbit, a spacecraft needs to reach about 7.8 kilometers per second. Achieving this requires carefully calculated burns to add the right amount of velocity. If the delta V is too low, the spacecraft might not reach orbit or could fall back to Earth. If it's too high, it wastes fuel and increases costs. Mission planners spend a lot of time calculating the total delta V needed for the entire trip. This includes launching, orbit insertion, and any maneuvers needed later. Keeping the delta V as low as possible helps save fuel, which means a lighter spacecraft and lower launch costs. It also means more room for instruments or fuel for future adjustments. During orbital insertion, a burn is usually performed at a specific point, like at the highest or lowest point of the transfer orbit. This burn adjusts the spacecraft's velocity vector, changing its trajectory from a transfer path to a stable orbit. The difference between the current velocity and the desired orbital velocity is the delta V needed. This change in kinetic energy is what pulls the spacecraft into its new orbit. If the target orbit has a different inclination, or tilt, from the arrival path, additional delta V is needed for a plane change. These maneuvers are more fuel-intensive because they involve changing the direction of the velocity, not just its speed. Sometimes, mission designers use gravity assists or higher altitude orbits to reduce the delta V required for these plane changes. In interplanetary missions, delta V is used to slow down or speed up the spacecraft for orbit capture around planets or moons. Precise timing and the right amount of delta V are essential to avoid overshooting or crashing into the celestial body. In essence, delta V is the measure of how much effort is needed to get a spacecraft into the right orbit. It controls how efficiently a mission can be completed and how much fuel is required. Understanding and managing delta V is fundamental in designing successful satellite systems and space missions.